Okay, so now that we've seen an example, some examples of like proving that there's a bijection between two sets, I want to talk a little more about this idea of bijections, and I want to really explicitly explain a key idea about bijections, and that is that bijections can be reversed and strung together to make new bijections. So let's take an example. Let's say this is a pretty general example. This is what I mean by this. If F is a map from A to B, and G is a map from from A to C, okay, so they're both mapping from A into different codomains, A to B and then A to C. If those are both bijections, well, then if I take the inverse of G, okay, G inverse is going to be a map from C to A, and that is also a bijection, because if you do one-to-one correspondence between two sets and then you just flip all the arrows around, you get a one-to-one correspondence going the other way. Okay, that's one of the key things about bijections from section 2.3 was that a function is a bijection if and only if it is invertible. And I didn't mention it at the time, but I think it's kind of obvious that its inverse is also going to be a bijection because it's also invertible, right? So, yeah. So you can take the G, you can inverse it, and then you can do, what do I want to do? Oh, you can do this. I'm sorry, I did the wrong one. I meant to do F. F is invertible and it is also a bijection, B to A. Okay, I could have done it with G, but I wanted to do it with F. And the reason I want to do it with F is so that I can string them together. I can go from B to A and then from A to C. And if I do G composed with F inverse, that is going to be a map from B to C, B to A, A to C, via composition, is also a bijection. So from this, we get this idea that if two sets are the same size, if you have two sets which are the same cardinality, and another two sets that are the same cardinality, and one of the sets they share in common, like if cardinality of A equals cardinality of B, and cardinality of A equals cardinality of C, then what we've just explained here with this idea about bijections being something that you can reverse and string together, it actually proves that the equality of cardinality is something that you can make this kind of deduction. Okay, you can say A equals B, A equals C, so therefore a B equals C, all right? Now you may have thought, well, why did you need to talk about bijections in order to say that? Well, if you've done any programming, you know that sometimes the definition of equality is different for different types of things, and the way that you define equality is what determines whether or not it has a property like this, right? Can you actually do this, right? When you like create a data type, you have to define what equals means, and you better define it carefully so that it acts the way you'd expect equals to act. And this is something we expect to work, right? This is something that should work. And so our definition of equality better support that. Okay, so all of the theory here is very like consistent and very robust in that it supports this idea, like the definition of equality, like the idea that I'll pull it up from the previous page here. Equality is defined as there exists a bijection between the sets. Well, that supports this conclusion. All right, so I just wanted to kind of lay that out very explicitly. Because it's not something we really have to grapple with very often, but it is, I think, an important idea just to have in mind. So with that, I next want to go over a couple of theorems about cardinality that are just sort of very general theorems that give us some pieces to work with, and it can make proving some things a little easier if we rely on these theorems. So let's start with this. If you have a set A, and A is countable, and if you have a subset of set A, well then B is also countable. The subset is going to be countable as well. You can't have something which is a subset of a countable set which itself is not countable. Like that's not possible. Okay, we haven't even really talked about uncountable yet, but we're going to very soon. Okay, so this is guaranteed. Now, another one is if you have two sets, A and B, if A and B are both countable, then in fact, so are the sets A union B and the set A cross B, the Cartesian product of those two things. So this is a little less obvious, but the union of two countable sets is guaranteed to be countable. One way you can kind of approach that is to say, well, if the two sets are completely disjoint, if the two sets A and B have nothing in common, then when you take the union, it's going to be kind of like you have double the number of elements, except not necessarily. But it's kind of like you have all of the elements of A and all of the elements of B, and those are all distinct. But what you can do is you can do a trick kind of like what we did with integers over here. So back when we were proving integers are countable, we said, hey, let's map our even numbers to one place and our odd numbers to another place, right? And we kind of divvied up the integers and said, well, map even numbers here, odd numbers there. And we kind of, we kind of got this alternating back and forth between positives and negatives as we go back and forth between evens and odds. And that idea, you can basically use that to prove this as well, because you can map all your even numbers to the elements of A, and you can map all your odd numbers to the elements of B, right? And that kind of just divvies up and makes it like this nice systematic way of counting everything in A as well as everything in B. It's not quite as simple as that because there could be overlap between the two sets, but that at least gives you an idea of why that might work. The same kind of thing is true over here with A cross B, except it's a little more complicated with A cross B. With this, you have to do this sort of like diagonal, it's sort of like a diagonal, like array, like two-dimensional array type of thing that you can build. That I'll show you how to do this in a couple videos from now, when I talk about in the next video, when we look at the rational numbers. So hold that thought, and then think about this A cross B after I've shown you rational numbers, and then I think you'll be able to imagine how you can prove that. So, all right, let's talk about rationals.